Hello and welcome back for another presentation, this one on earthquakes and faults. So if you've watched the previous lecture, we introduced the fact that we live on a dynamic lithosphere, that our planet is constantly in turmoil. We know this energy, its origin essentially, is from the center of our Earth within the inner core and is through the radioactive decay of uranium. It's through the decay of these isotopes. The byproduct is heat. That heat travels up into a convection cell, which essentially is the energy and fuel needed to move our plates around. So we learned a lot about that in the last video. We also learned that, like a dinner plate, we have boundaries around that dinner plate. It's very rare that you'd actually come across a plate boundary unless you're specifically looking for it, but living in California, we have an excellent example of a boundary. We have the San Andreas Fault that runs the whole length of California along the west coast. That is a transform strike slip boundary, meaning that it's pushed together and sliding. It's very conservative in that sense. It's not making anything new. It's not really destroying the old. It's just kind of sliding along. Well, like a dinner plate, if maybe you've seen like a really old one at a thrift store or something like that, and you'll see there's very small hairline fractures or weaknesses within the plate on the inside. Well, those are going to be your faults. Those are going to be your weaknesses within that rock. So this presentation here really is going to discuss faulting, the different types of faults, and the energy and how that whole process works. So let's just kind of jump right in. So at the beginning is, well, what is an earthquake? Well, an earthquake is, for many, a very scary thing. It's really just scary because it's unknown. Through extensive research and study, we're able to predict quakes between 6 and 12 seconds around there, knowing when the energy will be observed and felt by us, but there's still very, very unknown. We know a lot about it and a lot of the reasons why, but we just don't have we don't really know the moment when, and I'll give you a couple examples of that. What scares me about earthquakes, since we're being honest here, is not the quake itself. It's us, humans. Look at this office that I'm in at home. I've got all kinds of junk all over the place. Most people have junk too that's hung on the walls. They've got shelves and stuff like that. But do you have it adhered? Do you have it bolted? Right? When we have an earthquake, it's very rare that people actually get hurt by the quake itself. It's more of the stuff that we have. That's when people get hurt. So make sure you're responsible about that. But let's talk about this. So we live in a dynamic place that's constantly in motion under stress and tension. Well, when these blocks finally move, there's energy released. And that energy released that we feel is an earthquake. So I think of earthquakes kind of like tempers. So I can get a bad temper once in a while. I'm the type that stores all that pressure and stress and tension, and I let it build up, and then finally at some moment, over something very ridiculous usually, then I get all frustrated and I lose my temper, right? Well, think about this whole situation. You've got this plate, you've got all this stress and tension and pressure and all these things building up, and at some point it's gonna pop. And when it pops, that's when that energy is released, like a burst of your temper. And that energy that's released is seen in waves. And those waves are what we feel as being a quake. So seismologists record this movement or these waves. Two waves that we'll talk about for this course are going to be P and S waves. There's also surface waves, but just to simplify it for our cases, we're going to look at more of just the P and the S. So let's look at these images here that I provided for you. Here we have two pieces of rock material. We see that that rock has moved away from each other, so it must have dropped in that sense. So that being said, we have the hypocenter, or the origin of that energy, the epicenter where it was felt on the surface, and then we have the residual. What do we observe? We observe a fault plane. So this is kind of that process. Looking down here, P and S waves. When I think of P waves, I think of compression. You have that jolting back and forth, right? Very destructive. Now, S waves, I think of like a snake, because it's more of this type of wave. So when we experienced the Ridgecrest earthquakes in 2019, all the way out here in Los Angeles, we felt the S waves. We felt that rolling motion, and that's what we experienced. So we'll talk more about these things in a moment. Something else we'll talk about is the elastic rebound hypothesis. Now, this is actually quite interesting. I just kind of explained it as a temper, as when you build up that stress and tension. But this is an example. They're using a limber stick, a ruler, or a pencil. Again, earthquakes is that energy that's being released rapidly. That energy was stored up, so it's subjected to that force. At some point, the strength of the rock will be exceeded by the energy, and it will just break, and it snaps, right? So you can see that this is perfectly normal. They start to bend it, so they're applying energy, and most of the tension is being felt right here, and at some point it will rupture. And when it ruptures, here we have that slippage, we release that energy. So, of course, I wasn't here, I was prepared for this. Index cards. I always use index cards for everything. I write all my notes on them. I highly suggest it. Anyway, here's an index card. So let me just tear an index card kind of like this, real quick. I know, I'm not very good at tearing, but I did it on purpose, right? Because if you have an area where the two plates are nice and smooth, no problem. Slides back and forth, no problem. But like this image that they're showing, nice and smooth, right? But things don't work like that. They work like this, where things get stuck, right? So you have these areas of compression, and when those two corners get stuck, and it pulls and pulls and pulls and pulls, well, sometimes it does that, right? So when they're talking about the big one, we know that all this stress and energy is being built up in here in California. At some point, it's going to have to give out. It can't take it forever, and it will have to release it. That's what we're talking about. So that's that idea of elastic rebound hypothesis. So moving forward, how do we observe this? Well, we record it using many different scales. I'm going to talk about the Richter scale in particular. So Charles, or I like to call Chuck Richter out of Caltech in 1935. There's lots of different ways to observe this, but how can we actually relate the energy and to be able to compare them to one another? Well, he created a scale that looks at earthquakes by the name, also compares it to the energy equivalents. So, how do we do this? Well, you probably have heard of it, like a 4.0, a 5.0, a 6.0. Well, what does that mean? Well, it's a logarithmic pattern looking at the energy. So it's a value of 10. So you have a 1.0 and a 2.0. A 2.0 is 10 times greater than a 1. Then you go from a 2.0 to a 3.0. A 3.0 is 10 times greater than a 2. Or a 3.0 is 100 times greater than a 1. 4.0. 4.0s are 10 times greater than 3, 100 times greater than a 2, and 1,000 times greater than a 1. So when we start seeing these numbers jump from a 1 to a 2 to a 3 to a 4, we're looking at 10 times that amount of energy. It adds up quick. Imagine your bank account doing that, right? Every day your bank account was to increase by 10 times. Maybe you have $10 in it right now. That means tomorrow you'll have 100, and then the day after that you'll have 1,000, then you'll have 10,000, then it just continue 100,000, da 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 da. So it multiplies very quickly. So when we say that Ridgecrest here experienced an earthquake of large magnitude, somewhere almost to 7, is about a 6.5, we know that we're looking at tens of thousand times greater than just a 1.0. It's quite large, very large to be exact. So let's look at this real quick. So what they've done is I actually added Ridgecrest, so you can probably tell it's a different font because we haven't added. As you can see, the most recent earthquake is the one in Japan in 1995 on this diagram. So I thought I'd throw something a little more relevant. So I did my best I could. But looking at this, we're looking at the volume or total number of earthquakes. So 2.0s, we have globally over 1 million of those a year. We have them all the time. We just don't feel them because we're in motion, we're driving, we're walking, we're pacing, we're on bicycles. You don't feel that motion. If you just sat all day and did absolutely nothing all day, you'd probably feel some of these, but chances are you're not doing that. 3.0, 100,000, 4.0, 10,000 quakes. But look at the energy equivalent. So you have a moderate lightning bolt. 4.5 to 5.0 is average tornado. Looking at a 6.0, the energy equivalency is the same of the atomic bomb in Hiroshima. looking at what 7.8, we're looking at Mount St. Helens eruption, or an 8.0, the world's largest nuclear test in the USSR, or Krakatoa. So we start seeing that these, look how fast we go from a tornado to an atomic bomb to the world's largest nuclear test. So it's quite progressive. So it allows us to understand that. Now, what's neat about this as well, this might get confusing, and I apologize in advance, but if you think about everything like as a wave, so you have a 1.0. Think that it takes one chip to create that curve. Okay, like if it's a piece of elastic or string, so you put one chip, so that string can go like this. Then you have a 2.0, so you add two, so now you have a bigger curve. But then you have to add additional chips within it. So what ends up happening is, yeah, we're saying that a 1 or a 2 or a 3.0 has a lot more energy, but we're looking, it's actually more like 32 times more in that sense of just the sheer energy, not just looking at the magnitude of what it means. So all I'm getting at here in the sense is that if we think about, earthquakes in some form of a curve, when we go from a 1 to a 2 to a 3, it's incredibly large. It's a very, very big difference. So the people who lived in Ridgecrest and felt that earthquake, that had to have been terrifying because it's a really, really large earthquake. Or the people who lived through the 1906 earthquake in San Francisco, that is California's largest earthquake on record that we know of in recorded history. That had to have been absolutely terrifying to experience something like that. So we'll talk more about that too, just because again, it's the unknown and the amount of energy involved. But anyway, that's kind of how it works. It's a logarithmic pattern of 10, or 10 times, 10 times, 10 times. So let's look at seismicity and distribution. So this diagram I thought was quite interesting. It puts earthquakes, so whether it be shallow, meaning that they are felt on the origin is more towards the surface. We have intermediate, and then we have really deep earthquakes. We also have these little triangles that represent volcanoes. So here we have our ring of fire, which makes sense. So we have all of these very shallow earthquakes that occur also along this ring of fire. And that's because these areas here are divergent. So when you have new material being pushed up and moving away, there's going to be energy release. There's going to be some shaking. We see that there's some more medium and intermediate and then deep earthquakes that originate here, down by South America along the shoreline. Well, why is that along these very high mountains? Well, because the Nazca plate is subducting and going underneath. And as it goes underneath, it remelts, but it's being forced, it's being pushed, being stuffed in there. So you're going to be storing a lot of energy that way. You also see that South America is moving to the left. So you have two areas in which they're moving together like this, and he has some material that's being pushed underneath. So you have a tremendous amount of stress and energy that's being stored and observed. So I guess thought this was an interesting way to see it. Maybe as an example, the India plate, which is one of the fastest plates, that continent itself, that plate is its own piece. It's actually slamming into Eurasia, and at some point, geologically, if things continue the way that they are, the Indian plate will no longer exist. We'll just completely fold up into the Eurasia plate. But we can see that we have a lot of these shallow. Well, why is that? Well, because it's actually two continental plates pushing together, so there's no subduction. So we're not dealing with anything very deep. We have these two plates that are pushing and making mountains. So everything is happening in that compression zone where it's being push, 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 push. So anyway, I guess thought this was an interesting way to look at that distribution. Another thing that I wanted to point out, we have some volcanoes up here. This continent here is being torn apart in half, and there's fissure eruptions. Fissures are when you have crust that tear apart, and it's a wall of lava that shoots out. It's pretty cool. And then we also have all these volcanics in the Cascades and part of the Eastern Sierra. So we have all of that in here too, which is kind of cool. All right, so let's talk about faulting, which is part of the stress and the tension. So I got these diagrams. So we've been stuck at home for a while, so I did some online shopping. I bought a 3D printer because now they're quite affordable, and I have made some pretty stupid things recently because I'm learning how to use it. But I then was able to make something cool that I'm going to be able to show you, which are these two triangles. This is essentially going to represent a lot of this area. So I'm going to talk about each one of these faults as the picture that I have provided for you, and then I'll give you an example of what it would look like with these blocks. So the first one we'll talk about is in the top left-hand corner, which is considered a normal fault. So in normal fault systems, what we have is that the rock material is kind of being pulled away, and in that process, an area or part of it drops. So as an example, I don't know if I'm going to try to hold it this way. So you can see that there are some letters. So if I want, say, letter B to line up with A, see how this had to drop down to match that area? Well, this would be a normal fault. When we see that the material has been pulled down, it's been dropped down, that creates a normal fault system. It's normal for things to be pulled apart, okay? The next one, letter B, on the top right-hand corner, is a reverse fault, which means it has to be the opposite. So if normal faults brought it down, reverse must be where it's pushed up. So where my letter C goes to letter D. So it's being thrusted up, it's being pushed up. And that would be a reverse fault. We also have I'll move here, letter C. This is still part of this system. It's called a thrust fault, but instead of it being lifted up, it's actually sliding a little bit differently, as you can see. Here in letter B, you can see that these layers of material are no longer continuous because it's literally just breaking apart and being pushed up. Down here in the thrust fault, we can see that these areas, there's still a very distinct line within the rock material, but the whole sheet is being kind of pushed up as a whole. So I guess it would be something more, if I wanted to kind of represent it this way, it'd be more like this, where it's actually sliding across, but that's not what this one's designed for. And then the last one is a strike slip or shear, where it's actually just sliding back and forth. So in that case, if I wanted to look at the model going this way, see how I have two other letters? I have an F and a G on the top. So if I want to bring the G down to F, see how I can move it back and forth side to side? So it just breaks the road. Well, in that same process, looking at it this way, what's interesting is if I move them this way, you really can't tell because the layers are still continuous. So as an example, some of the faulting that was observed in Ridgecrest, there's a lot of those faults are part of this strike slip system, where we actually see the roads have been split like this, which is kind of cool. Again, looking at now there's a road, if things move up or down, if you're driving on this road, it'd be a cliff, right? Well, what if there's water on the road? You'd have a waterfall. Or what if it was going this way and the water was flowing here? Well, the water would hit the wall and turn into a lake. So we find there's so many different variations of what can happen with our faulting within our surface. Well, we've mentioned a lot about faults. Let's talk about one. Here is the pictorial of the San Andreas Fault. Remember, I had my index card paper that I threw in the air, showed you this area of compression. Well, this area of compression right here, as you can see, occurs. Yeah, this is part of the San Gabriel Mountains over here. This is the Garlock Fault. So we actually live pretty near it in Santa Clarita, where it kind of merges. So the Garlock Fault matches up with part of the Pelona uplift, which is where Vasquez Rocks is. So we see all these different faulting zones. These are actually faults that are the result of the San Andreas. It's part of that energy that's being dispersed. So most diagrams show the plate moving like this. So you have one area going up, one going down. It's not really moving down. We use these arrows to show where the tension is. They're just moving at different rates. But nonetheless, this is kind of the vision that we have. So we can see that the Sierra Madre Fault, we can see that here this is more of where we live. Taking this image, rolling it over here into this diagram, these are major faults. Major faults. Are there others? Lots more. But most of them are quite small. So here's the Santa Monica Fault, which I think is interesting. So these are the Santa Monica Mountains, and actually you can follow the Santa Monica Mountains all the way out to the ocean in the Channel Islands. The Channel Islands are actually part of a mountain range. Now they've just been submerged in water. Here's the San Andreas Fault, the San Gabriel Fault. So the San Andreas Fault, this is the San Gabriel's, which is like where Pasadena is. So this is on the other side of those mountains. And then we live over in here. Here you can take the Garlock Fault out to go this way to Owens Valley, which is how you go up to Reno or Mammoth. So here we have Panamint and then Death Valley as well, which is interesting. Owens Valley, this is Mount Whitney, the tallest point in our state. And then Badwater Basin's down here, and that is the lowest point. So between these two distances, as you can see by this graph here, is about 100 miles. And this is 14,508 feet, and then this is negative 282 feet. So there's quite a dramatic difference between the elevation in both of those places. And it's why? Well, because of faulting. It's because of the dynamics that we see. And we'll talk more about that in a moment. So I just want to kind of put it in perspective. I think it's interesting also, since we're looking at this map, where you think of your population. Where do people live? People live along faults. We live all along the coastline and all along these cities. Think of all of our big cities. The Hayward Fault is a huge fault. But looking at all these different, this is where everyone lives, right? Think about areas out here in the middle of nowhere. Out here in the middle of nowhere, no one lives out there. Well, because we find that faulting creates the mountainscapes and the valleys, and creates the landscapes that we want to live in because they're pretty. But like all things, there's going to be some form of, with all good things, there has to be a but part. Well, what if, or a but? It's good, but you got to deal with this. Let's talk about two earthquakes. This one, I'm sure you remember it. I'm kidding. It's the 1872 Lone Pine earthquake. We don't know how big it was because at that point, we really didn't have, we were studying earthquakes, but we didn't really have a way to measure the energy. The only thing that we can do is we can measure the energy based off of the displacement. So what does that mean? Well, let me back up. This is, we think, many of us argue that this could have been bigger than the San Francisco earthquake of 1906. We just don't know. But I think it probably was. We believe it was between a 7.6 and an 8.0. The why? Well, the result. Why do we think it's bigger than San Francisco? The result was a vertical uplift, meaning the Sierra Nevada lifted 20 feet in the air in just a few seconds. And we also observed a right lateral movement of 40 feet, which means that, if I use this model as an example, so we find that it went up like this, and then it moved to the right by 40 feet. A 2-car garage is about 20 foot, so you're moving about a 4-car garage plus in seconds. It was so big. How big was it? It was so big that John Muir, who was living on the other side of this mountain range, on the other side of the Eastern Sierra over in Yosemite, it threw him off of his bed and he hit the ground. It was quite huge. It was felt as far north as Sacramento. It was felt all the way down to San Diego, and felt all the way eastward as in Elko, Nevada. What was interesting about that as well is that this is a terrible diagram, but the Lone Pine area is known for its fault block valley of horsts and grabens. Horst because these areas, this is the Sierra Nevada, this will be the Inyo Mountains, they're hoisted up because of faulting. But then the valley itself is actually dropping. So these little arrows we use in geology to show direction. So we know that at one point this was up in here, but there's been that much differential moving. I hope that makes sense. Let's look at something a little more recent, but still probably something you don't remember, but I remember vividly. Oh, that reminded me. I was going to show you a bottle. I think I left it in the garage. Ah, shucks. Well, I'll explain what it is anyway. So the 1994 Northridge earthquake. So I remember this well because I grew up out in Baldwin Park, and we actually moved out in the end of 93, just in time to experience this in Santa Clarita. So it was centered near Northridge on January 17th, and it was measured of a magnitude of 6.7, and they felt it as far east as Las Vegas. Now, the damage from this earthquake was between 13 and 15 billion dollars by today's value of money, about 22 to 86 billion. It's kind of, there's some variations. Making it up to that point one of the costliest natural disasters in history. So it was incredibly devastating. Perhaps you recognize this is the 514 interchange. What's interesting about the main shock that was felt, the 6.7, is that there were actually 2 aftershocks that were of 6.0. So afterwards, which is pretty impressive. So we had 3 of them technically in a row, right? So you have what's considered the foreshock, which is happening before, if there's one. Then you have the main shock, and then you have an aftershock. What's interesting with those words, fore, main, and after, is that the Ridgecrest earthquake they had a big quake, and they said, wow, that was really big. And then later they had even a bigger one, which means that big one they thought they had was actually just a warning to the much bigger one that they had, which is kind of interesting. So this photo here, bottom right here, this is perhaps you've been. There's actually part of these columns that still remain in a garden. This is the parking structure at Cal State Northridge. So again, centered right out there, which is why also they've been undefeated football team since 1994 because they haven't had a football team since then. So very, very large earthquake that was more central to where we are in Santa Clarita. Well, let's look at some features real quick. So I think this is an interesting. I pulled this up out of Google Earth. So these are called sag ponds. So a sag pond, like sagging, like I don't know, like a dog's jowls, how it sags. This red line represents the San Andreas Fault. This, perhaps you remember, this is the 14 freeway. You've probably driven out to Palmdale, and there's a big windmill out here, and this is Lake Palmdale itself. So this lake is the result of essentially when you have strikes up areas. Some points you're going to have a depression that's going to accrue, and that depression will result in a pond or a lake. And so we find that this is a very common feature along the San Andreas Fault. We've all got these little small lakes along these strike slip boundaries. If you've ever been along the Eastern Sierra, so you've driven this road, the 14 to 395 all the way up, there's a place called Diaz Lake along 395 on the western margin of Owens Lake. Diaz Lake is another sag pond. So you have where you have the earth moved, and in that movement you actually end up creating a depression that can then either perhaps it taps into an aquifer or some form of underground stream discharge. Is able to fill it, or then it's just regulated by people. So that's one feature. Let's look at a shutter ridge. Excuse me. So these occur where the fault carries high ground on one side. So here we have the Garlock Fault. This river at one point would have been a straight line, but see how this side has moved over to the right. So it's actually shifted the way this river operates. So this is what we consider a shutter ridge. So the rocks move to the right, blocks the stream, and the stream will have to find the path of least resistance to continue to flow. We also call this an offset stream, which I thought was kind of cool. The name Shutter Ridge, which I thought was kind of interesting, actually originates from the old cameras that had the shutter that would, inside to let the exposure in. That's where the name came from, because it actually shuttered like as just like a quick slide and like a camera opening up its aperture. So that's a shutter ridge. And then fault scarps. Fault scarps are observed very often. So this is Tectonic Landforms Fault Scarp. So here's this really bitchin' card up here looking at this ridge. This is the result of the 1959 Hebgen Lake earthquake in Montana. So they walked out to this the next day. So it moved that far. So, using this gentleman as some form of scale, we're looking at probably a 10 to 11 foot difference. So at one point these would have been at the same level, but there was that big of a change. So it's what we consider an offset. And then the fault scarp, a scarp is like a scar. So we actually can see it on the landscape. The image to the right, I said that already. The quake was so large it actually caused new geysers to sprout up in Yellowstone National Park, which I thought was pretty interesting. Whew, so we covered a lot of information. So we talked about the different types of faults. Remember, I used my little model here to represent whether it be a normal fault system, or maybe it's a reverse fault system, or perhaps it's even a strike slip. So again, these are small fractures in the Earth's crust. So when yes, this is compressional, a reverse fault, absolutely, but we have to consider it as a smaller scale. We have to separate plate boundaries, right? You have to separate the perimeter of the dinner plate from what's occurring on the center part of that plate. So that's where it does get confusing, because it's like, well, why do we have earthquakes in Kansas when there's not any plate boundary near it? It's like, well, because you have these hairline fractures of weakness caused by stress and tension and pressure. That's why those things even occur. So anyway, I hope that really helped explain a little bit. We talked about the three mains. I also mentioned horsts and grabens as well. Those. So we technically, I guess, mentioned 5 different fault types, which is pretty cool. There are a couple others, but I'll leave you with that. If you're interested in them, you should certainly look them up because we can also have what we consider oblique, where it actually can move down into the side at the same time. That's really what we experienced a lot in the Eastern Sierra during their large earthquake. But maybe you remember the 94 earthquake. Maybe you were there. Maybe you remember an earthquake more recently. So be sure to comment that below. I'll have to share later. Because I'm old, going through the garage, I found the original cans that the breweries, the local breweries, stopped producing beer and started bottling and canning water because in Santa Clarita we didn't have any drinkable water available to us after the 94 earthquake. So we were all given cases of beer cans that only had water in them. And I remember going to school with my Budweiser can that said water on it. It felt pretty cool. But anyway, I hope you enjoyed as much as I did. And if you remember, be sure to comment below. Otherwise, don't forget to click and subscribe, and we'll talk soon.